Greetings. In today's lecture, we're going to introduce the concept of limits. Now, when I first learned limits, I kind of wondered what they could ever be used for. They seemed kind of simple and obvious, although sometimes the notation can be complicated. However, as it turns out, the whole notion of a limit is one of the most essential ingredients in establishing the theory of calculus. So without further ado, let's take a look at the basic intuitive idea behind limits. So the idea is, so we would write it like this: the limit as x approaches c, so it's a little arrow there, of f of x is equal to L. So this is the notation, and then we would read this as the limit as x approaches c of f of x equals L. And what this means is that the values of f of x are becoming closer and closer to L as the x values are becoming closer and closer to c. So this means, let me write that down, the values of f of x are becoming closer and closer to L as x is becoming closer to c. So basically, as you move the value of the inputs closer and closer to the point c, the outputs are approaching the number L. Now, there's a few things that should be noted. One, it does not matter if the function f is defined at c. So in other words, f of c might not even be defined, and yet we can take the limit as x approaches c. The second point to keep in mind, even if f is defined at c, so even if f of c exists, in other words, even if f is defined at x is equal to c, the value f of c in no way affects the limit as x approaches c. So in other words, what's happening at the point c is completely independent of the limit. In other words, when you're asking the question, what is the limit as x approaches c of f of x, the actual value at x is equal to c is irrelevant. So you don't consider that at all when computing the limit. And so in this way, what the limit actually does is it gives us a way of quantifying the behavior of a function not at the point precisely, but as the x values get closer and closer to a given point. And this is very useful whenever a function is not defined at that point, or when there are holes in the function or jump discontinuities. So then you have different things going on. So let's take a look at some examples. And let's just look at a few graphs first. So suppose we have a function that looks like this. 1, 2, 3, 1, 2, 3, 4, 5. And at the point 3, 5, we have a hole in the function. And we have a function like this. Now, the function is not defined at x is equal to 3. So f of 3 is equal to nothing, because so f of 3 does not exist. Does not exist. But yet we can say something about what's happening to the function as the x values get close to 3, right? So as the x values become closer and closer to 3, so we're moving in from the left or from the right, we might take an x value like this and compute the output, we might get 4. We take an x value a little bit closer to 3 and we get 4.5. We go even a little closer still and we get 4.9. If we keep choosing these x values closer and closer to the point 3, we're getting outputs that are becoming closer and closer to 5. So there's exactly a gap right here. Another way of thinking of this is if you were to make the function continuous at x is equal to 3, you would have to fill it in with f of 3 is equal to 5. So what we have is we say the limit as x approaches 3 of f of x is equal to 5. So all this means is that as x values become closer and closer to x is equal to 3, the y values are getting closer and closer to y is equal to 5. Let's take a look at another example that involves an actual equation. So this one, f of x is equal to sine of x divided by x. And note that this is not defined at x is equal to 0. Because if you were to attempt to plug in the value x is equal to 0, you would get 0 divided by 0, which is not a number. And so in this example, we just want to look at what's happening as the x values are getting closer and closer to the point x is equal to 0. So the question would be, determine the limit as x goes to 0 of sine of x divided by x. So we can look at a graph of this function, and I'll show you what the graph will look like in a moment. But first I want to actually just compute this computationally. So I'm just going to evaluate the function for smaller and smaller and smaller and smaller values of x and see what happens, right? Does this ratio go to infinity? Which it might, because we have something divided by 0. Or does it go to 0 because we have a 0 on the top, or does it go somewhere else? Let's take a look. So let's make a table. So we have some x values and then some outputs. So we have sine of x over x. And of course, it's important to be in radian mode, right? So unless otherwise specified on a few rare occasions at most, maybe never, we'll always want to treat trigonometric functions in radian mode. So for our values close to 0, let's look at 0.1, 0.01, and 0.001. And let's just start off with that and see what is happening. So if I compute 0.1, hit the sine button, and then divide it by 0.1, I get the following. So the output would be 0.998334166. Okay, now let's get a little bit smaller. 0.01 sine divided by 0.01 is equal to 0.999983333. Okay, now let's look at 0.001. 0.001 sine divided by 0.001 is equal to 0.999999833, and so forth. Now, you might be tempted to start off with a ridiculously small number, and in this case, I think it wouldn't be a problem. Sometimes it is. Let me just do one more. Okay. Yeah, sometimes what happens is if you start with your value too small, say 10 to the minus 10, your computer only, or your calculator, whichever you're using, only keeps track of so many decimal places. And so information can get caught or cut off if you have a very small value of x, and then you can end up with the wrong answer. So it's really good to get into the habit of looking at what's happening as you choose smaller and smaller x values and not trying to shortcut to just one super small x value. So if we keep this up, 0.0001 sine divided by 0.0001, my calculator says 0.999999998. So what you're seeing is as we're allowing the x value to approach 0, so x is getting smaller and smaller and smaller and smaller and smaller, the outputs are getting closer and closer and closer and closer to the number 1. So what we say is the limit as x approaches 0 of sine of x over x is equal to 1. And if you want to look at a graph of this function, it looks like this. It's supposed to be symmetric, but this is the graph of sine of x over x. And you see that there's a hole in the function exactly at y is equal to 1. So if you were to fill in the function at that point, you should choose f of 0 is equal to 1. So moving on, we're going to discuss something called one-sided limits. So there are two sides. So there are two types of one-sided limits. And the first one, we would say limit as x approaches c from the right of f of x. So that's a small superscript plus sign is equal to r. Or the limit as x approaches c from the left. So that's a superscript minus sign of f of x is equal to L. So I used R and L just for right and left. And so we would read this, the limit as x approaches c from the right, and then the rest of it, so of f of x is equal to R, or the limit as x approaches c from the left. So either from the right or from the left. And what this means is that instead of thinking about the function f on both sides of the point x is equal to c, we only look at the values of the output for either x is less than c or x is greater than c. So we only consider portion of the domain, and for the limit as x approaches c from the right, we would choose values of x greater than c. Right? So we're to the right of the point x is equal to c. And then as x approaches c from the left, we would choose values of x that are left or less than c. So let's look at a graphical example of this. It's supposed to be a straight line. That's better. So we have the point 5 here. We have 1, 2, 3, 4, 5, 6. And let's draw a few grids so we can see what's happening. So the function looks like this. So something like that. And then the function does this, like that. So this is what the function f of x looks like. It's a weird looking function. Notice though that it does satisfy the vertical line test, right? So it's probably not easily described by an equation, although it might be described by a piecewise defined equation. But for any x value, there's only a single y. And at the point x is equal to 5, the output is 3. So we would say f of 5 is equal to 3, right? Because 5 matches up with 3. And these holes indicate that, that's not part of the function right there. Now, as we approach 5, we get a different behavior depending on whether or not we're looking on the portion of the domain with x less than 5 or the portion of the domain for x greater than 5. And that's why we would use a one-sided limit. So if we look at the limit as x approaches 5 from the left, let's see what happens. So from the left, let's say we look at 4, we would get an output maybe 2.2, 4.5, an output of maybe 1.5, a little larger value but still less than 5, larger value, still less than 5, keep getting closer to 5, 1.1, get a little bit closer to 5, 1.01, 1.001, and so forth. And we're basically at this limit where right here, we can't actually evaluate, well, if we evaluate f at 5, it jumps up to here, but as we keep getting closer and closer in the x value to 5, but always using x values less than 5, the outputs are becoming closer and closer to the value y is equal to 1. So what we say is that the limit as x approaches 5 from the left, so I put a little minus sign there, of f of x is equal to 1, meaning that as the x values get closer and closer to 5 while staying less than 5, the y values are getting closer and closer to 1. Now similarly, if I look at f of 6, I might get something like that. If I look at f of 5.5, I get 3.5, 5.2, I get 3.8, 5.1, I get 3.9, and I'm getting closer and closer and closer to 4, right? So as x decreases toward 5, 5.1, 5.01, 5.0001, the y values are getting closer and closer and closer to 4. So the limit here would be 4. So we say that the limit as x approaches 5 from the right of f of x is equal to 4. So here's an example where the limit as x approaches 5 from the left, from the right, and then the actual value, f of 5, all give 3 different answers. So then finally, let's look at limits at infinity. So we say that the limit as x goes to infinity of f of x is equal to L if the values of f become arbitrarily close to L as x gets larger and larger and larger. So in other words, if x is sufficiently large, in other words, if x is large enough, at some point, the y values will be as close to the point L as you'd like. So let's see a picture of this. So there's x, here's y, and in red, let me just take a y value, extend it. So that's the line y is equal to 5. And let's draw a function that has the property that limit as x approaches infinity of f of x is equal to 5. Now the function starts out, and it might not have anything to do with y is equal to 5. So we might already be at 1 billion. But then once we pass a certain point, we're within a certain vertical distance to 5, and we'll never, there's always, for any vertical distance like this, far away from y is equal to 5, there's always some point that once you reach a certain x value, you'll never leave that distance from y is equal to 5. You might go back and forth, but you're never going to get farther away than, like, say, this, right? So at this point, maybe you're in some sort of tube, and for all, it might take billions and billions and billions of x values to get into that tube, but what the limit means as x goes to infinity of f of x is equal to L is that for any size tube like this around y is equal to 5, eventually you'll enter that tube and you'll never go out. It might take a long time for that to happen. And then of course that's true of smaller tubes. So here I'm already in a smaller tube, so I'm never going to come out. And it doesn't matter how small the tube is, right? I'm eventually, for any size tube, never going to get out of that tube. So that I might not actually ever, here you see that the f values are equaling 5 once in a while. I might not actually level out, but I'm always going to get closer and closer and closer and closer to y is equal to 5 as x gets larger and larger and larger and larger and larger and larger like that. So we say the limit as x goes to infinity of f of x is equal to 5. In all variation, we can say the limit as x approaches minus infinity of f of x is equal to L. And this is the same picture, except instead of as x goes to plus infinity, you have over here x getting more and more negative. So it's the other direction. But other than that, it's pretty much the same concept. Let's see an example of this. So let's compute the limit as x goes to infinity of 1 over x. So we all know what the graph of 1 over x looks like. So we have a vertical asymptote that comes down like this. Then it gets smaller and smaller and smaller and smaller. Now for no x value, will the output equal 0? But for any y value close to 0, whether it's 1 divided by a googol, which is a very, very small positive number, eventually there's going to be an x value where that output will be as close to 0 as 1 over a googol, or 1 over a googol plex, or whatever, however small you want to make it. This gets closer and closer to 0 as x goes to infinity. So we say that the limit as x approaches infinity of 1 over x is 0. Another example. So we saw an example where we had the heat of or the temperature of an object was given by. So this was the result of Newton's law of heating and cooling. And here, U0, R, and A are all parameters. And then A is a positive parameter. Well, we know that e to the minus at will shrink to 0. In fact, we previously saw the behavior of this. So basically we have R. There's u is equal to r, so this is the u-axis and the t-axis. And then we had u0. And basically this function looks like this. Just exponential decay towards r. So we never actually quite gets there. Because for any positive value of t, e to the minus at will be some positive number. So you'll get smaller and smaller and smaller numbers. It's always going to be r plus a number very, 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 very small. And as t gets larger and larger, this number gets closer and closer to 0. So this term goes to 0, and the r stays put. And so we say, in this case, for this function, we would say that the limit as t goes to infinity of u of t is equal to r. Next, let's look at a few more examples involving rational functions. A rational function is just a ratio of two polynomials. Now there are three main cases, and when you take the limit as x goes to infinity of a rational function, there's always a simple way to see what the limit is. So first case is when the top and bottom, so in other words the numerator and denominator, both of the same order. So for example, limit x goes to infinity of 3x to the fourth plus 5x squared plus 17 over 12x to the fourth plus 8x cubed plus 2x. Now in the numerator we have a fourth order polynomial, and in the denominator we have a fourth order polynomial. So as x goes to infinity, two polynomials of the same order will go to infinity at the same rate. And the way to determine the limit is to look at the ratio of the leading coefficients. So when you have a polynomial, like the numerator here, the leading coefficient is just a coefficient of the highest power. So the leading coefficient of the numerator is 3. Similarly, if you look at the denominator, the leading coefficient is 12. So when you have like powers, and these are like powers because we have 4 is the highest power in the numerator, and 4 is also the highest power in the denominator. So in that case, the limit is just the ratio of the leading coefficients, 3 over 12, or 1 over 4. One way to see this is to multiply and divide both the numerator and the denominator by the reciprocal of the leading power, so 1 over x to the 4th. Now notice I haven't changed it. I just multiplied and divide by the same thing, so I have not affected the limit here. So then when I distribute this, when I factor this in, I get the limit as x goes to infinity. Now 3x to the 4th divided by x to the 4th is just 3. Then plus 5x squared over x to the 4th is 5 over x squared, and then plus 17 over x to the 4th. Then divided by, on the bottom, similarly, we have 12 plus 8 over x plus 2 over x cubed. Now we can see what's happening, because as x goes to infinity, 5 over x squared and 17 over x to the 4th are getting smaller and smaller and smaller and smaller and smaller, and 3 is just staying the same. Right? So if you don't have your glasses on, 3 plus 5 over x squared plus 17 over x to the 4th looks pretty close to 3. Right? If x is equal to a googol, 5 over 1 googol squared is ridiculously small. And 17 over 1 googol to the 4th is ridiculously smaller. So we get something very, very close to 3. 3 followed by 10,000 zeros and then some stuff. And similarly on the bottom, we would have 12.100 zeros and then some stuff. And then as x gets even larger, way beyond a googol, it's just getting closer to 3 and closer to 12. So you can see that the limit would be 3 over 12. So that's what you do when you have polynomials of like powers on the numerator and denominator. Now, if you have polynomials of different powers, so like say limit as x goes to infinity of 3x to the 7 plus 8x to the 5th plus 27 over 4x5 plus 83x squared, whichever polynomial has the highest power wins. So if the highest power is on the numerator, the whole thing goes to infinity. And then if you do the opposite, 3x to the 5th plus 88x squared over 2x to the 6th plus 0.1x squared plus 0.001, the highest power in this case is in the bottom. Right, it's right here. X to the 6th beats x to the 5th. So the bottom is becoming larger at a faster rate than the top. So you're dividing by larger and larger and larger numbers, and the whole thing goes to 0. So that's what you do if you have rational functions with polynomials that are not the same order in the numerator and denominator.